By the end of this PowerPoint, you're going to sit an assessment. It's an achievement standard worth 4 credits at level 3, so that's pretty awesome. What you need to learn through this PowerPoint are the learning outcomes that you'll see on this particular slide. If at any point in doing this PowerPoint you get stuck or you want someone to help you understand something a little bit better, just give me a yell. Grab your teacher. I will help you out. That's what I'm here for. This PowerPoint isn't about you just working by yourself and learning all by yourself. It's just a way for you to be exposed to some new learning and then grab your teacher when you need some additional help. A variable is something that can be measured. The measurement describes the thing being measured. For example, height is a variable. My height is 169 centimeters, and this describes something about me. A variable is also something that can be observed, and it describes the thing being observed. For example, hair color is a variable. My hair color is dark brown. A variable is also something that can be counted. The number of siblings you have is a variable that describes you. I have 2 sisters. You now know 3 variables that describe me: my height, my hair color, and the number of siblings I have. Thinking about the variables on the slide above, which variables can be measured? Which variables are observations? Which variables are counts? On the previous slide, you were asked to identify the variables that could be either measured or observed or counted. So here they are again on this slide, and the variables that can be measured are weight, foot length, and time it takes to run a kilometre. Did you get those ones right as the ones that could be measured? The variables that can be observed and described are eye colour and favourite car. Did you get those ones right? The variables that can be counted are number of fingers. Each type of variable, measured, observe, describe, and counts, they can be categorized into groups. Variables are either categorical, discrete, or continuous. Categorical variables, think of the word category, are variables like eye colour and favourite car. Discrete variables are things like number of fingers. Continuous variables are weight, foot length, and time it takes to run a kilometre. The easiest way to tell the difference between discrete and continuous variables is to ask yourself whether something has been counted or measured using equipment. If it's been counted, the variable is usually discrete. If it has been measured, the variable is continuous. So for example, you'd count the number of fingers. You wouldn't measure the number of fingers using a ruler. Also, usually discrete data can't be chopped in half, so you'd never have 2.5 fingers. Well, you'd hope you don't have 2.5 fingers. So in those variables above, which variables are discrete, which are continuous? Now what we're really interested in for this particular achievement standard is just the continuous variables. So we're going to be learning about bivariate data, which means an object that has 2 continuous variables that describe it. Two variables that describe a human being are height in centimetres and weight in kilograms. We would expect a taller person to weigh more than a short person because they've got more bone, muscle, and skin, for example, than the shorter person. We can say that the height of a person explains their weight, or put another way, we could say a person's height is related to their weight. As a person's height changes, so does their weight. There's a relationship between height and weight. Do you get the picture? When a change in one variable explains a change in the other variable, we call it an explanatory variable. Explanatory sounds a bit like explain. Thinking about the relationship between height and weight, height is an explanatory variable because a change in height explains the change in weight. This is shown by the image in the above slide. Height measurements are along the bottom of the chart, and weight measurements are up along the side. The height measurement gets bigger as we go left to right. The weight measurement gets bigger as we go from the bottom to the top. Overall, the chart shows how height and weight are related, because a taller person, say 6 foot, can weigh 12 stone and be considered healthy, whereas a shorter person, say 5 foot, if they weighed 12 stone, they'd be considered obese. You have to note that this chart is not very accurate at deciding whether someone's healthy or not, so please don't use it to define yourself. You're fabulous. Full stop. Have a look at the group of children in the image above. They're all the same age, but look at their different heights. Genetics and environment work together to determine a person's height. This is why not every 6-year-old is the same height. This is called natural variation. There's a natural variety in heights. How tall will your baby be? Use the height predictor on the link above. Do you notice how the prediction of your child's adult height is a range of values, not just one single value? This is called a prediction interval, and it means that the prediction will be more accurate. It's better than saying your child will be this tall, because, that's not likely to be correct. It'll be somewhere between a range of values. If we measured the height of 100 6-year-old boys, we would see the natural variation in their heights. If we plotted their heights on a dot plot, we would find out a range of heights that are the most common for that group of boys. If we designed jeans for Pumpkin Patch, we'd be very interested to know the typical height range of 6-year-old boys in New Zealand, so we could make jeans that were the right length. Usually, the purpose of any statistics investigation is to explore natural variation in a population of individuals. To get an accurate idea of what's happening in the population, we need to make sure the way we measure each individual in the population is done the same way. This is so we can compare all the measurements and know that any differences we see in the measurements are due to actual differences in the individuals and not because of differences in the way we measured the individuals. Look at the picture above. Both children are having their heights measured. The height of child A is 105 centimetres and the height of child B is 110 centimetres. Is the child B actually taller than child A? So on the last slide you were asked to have a look at the two children with their heights being measured, and it asked you if it was a fair way to compare their heights. How could they improve the accuracy of their height measurements? So in blue on the slide that you're looking at now, it gives some ideas about how they could improve the measurements so that both childs were being measured in exactly the same way. If they weren't measured in exactly the same way, then comparing their heights is a little bit rubbish, because one could be not standing up straight, or the other could be tippy-toeing or wearing shoes, etc., and so their measurements don't reflect their actual height. So one of the things you need to do when you're measuring is making sure that everything you measure is measured in the same way. Organisation is the key to a good statistical investigation. Record your measurements in a tidy, clear, easy to read table, just like the one that's on the slide you're looking at. This helps you avoid errors in recording the measurements. This will also make it easier for you to transfer your measurements to Excel ready for data processing. Bivariate data is displayed graphically as a scatter plot. Put simply, you make a graph, it's called a scatter plot, and you put your data on it. A graph is an image that helps you quickly see if there is a relationship between two variables you've measured, for example, like height and weight. On the above slide is an example of a scatter plot. Each dot on the scatter plot represents one day. Each dot tells us two pieces of information about that day: the temperature and the number of visitors at the beach on that day. For example, The dot on the far left had a temperature of 82 degrees Fahrenheit and just over 75 people visiting the beach. It makes sense that more people will visit the beach if the weather is warmer. Temperature is the explanatory variable because the change in temperature explains the change in the number of people visiting the beach, the response variable. The explanatory variable is always plotted on the x-axis of the graph. That's the bottom of the graph. And the response variable is always plotted on the y-axis, which is the side of the graph. The graph shows that more people visit the beach when the temperature is warmer. Check this by comparing the number of people that visit the beach when the temperature is 84 degrees compared to the number of people that visit the beach when it's 96 degrees. When deciding which variable is the explanatory and which is the response, you need to consider both variables together because it's about their relationship. Temperature is the explanatory variable in the above example, but it could be a response variable if we're looking at the relationship between cloud cover, the amounts of clouds in the sky, and temperature. It makes sense that the more clouds in the sky, the colder the temperature might be, because the sun can't shine through the clouds to warm the earth. In this case, a change in cloud cover explains the change in temperature, and the temperature is the response variable. A scatter plot gives you a picture of the relationship between two variables. It shows you what happens to one variable when the other variable changes. What a scatter plot does not tell you is whether one variable caused the change in the other variable. For example, many factors influence a person's weight, not just their height. There's a relationship between height and weight, but height increase alone does not cause a weight increase. There's a methodical step-by-step process that you will learn and use so that you can interpret a scatter plot and use your interpretation to answer an investigative question. You'll look at the shape of the scatter and decide if there's a linear pattern, a pattern that looks like a line. If there is no linear pattern, you'll have to measure different variables and collect different data. Bummer. So hopefully you've found a linear pattern. If there is a linear pattern, there is a relationship between the variables, and the next step is to describe that relationship. You will look at the direction of the line to describe the change in both variables. You will look at how the dots are scattered to describe the strength of the relationship between the two variables. And you will look at how the dots are scattered to decide if the scatter is uniform or the same across the whole data set, or does it vary. You will look at the dots as a group and decide if there are any dots that are far away from the rest of the group and are unusual. Now you'll watch a series of videos that will show you how to interpret a scatter plot using this step-by-step process. Have a look at the graphs on this particular slide. Which ones show a linear pattern? Write down the ones that do using the letters that are related to each graph. For example, A, B, C, D, E and F. On the next slide are the answers. See if you can work it out before you cheat and look at the next slide. Good one. So here's the answers to the previous slide's questions. If you get any of these wrong, can you please just grab your teacher so I can explain something to you a little bit better? Thank you. Which of these graphs shows a positive trend, the one on the left or the one on the right? Which graph shows a negative trend, the one on the left or the one on the right? Answers on the following slide. Dun, dun, dun. If your two variables form a linear pattern on a scatter plot, it means there is a linear relationship between the variables. A change in one variable relates to a change in the other variable. We're interested in the direction of that relationship. As one variable increases, what does the other variable do? Look at the explanatory variable. As it increases, does the response variable also increase? If so, this is a positive trend. The graph on the left above shows a positive linear relationship between the variables. There's a relationship between husband and wife's ages. The older the husband is, the older his wife tends to be too. Looking now at the graph on the right, as the explanatory variable increases, the response variable decreases. Check this. Look at how much gas is used when the temperature is 20 degrees compared to when the temperature is 70 degrees. There's a relationship between mean temperature and gas used per day. As mean temperature increases, gas used per day decreases. This is a negative linear relationship between the variables. A positive trend looks like uphill from left to right, whereas a negative trend looks like downhill from left to right. The strength of a relationship describes just how closely linked a change in one variable is to a change in the other variable. This is shown in the scatter plot by how close the dots are to the trend line. The closer the dots are to the trend line, the stronger the relationship between the two variables. It can seem difficult at first to decide on the strength of a relationship just by eyeballing the scatter. You'll get better at it with practice, which is why the next slide is a wee activity for you to do. Why do we care about strength? The stronger the relationship between the variables, the more accurately any prediction made using those variables will be. We can predict a response value for any value of the explanatory variable using a scatter plot. The accuracy of this prediction depends on the strength of the relationship between the variables. Here's a few different graphs with different scatter plot patterns in them. See if you can work out the shape, direction and strength of each of these graphs. Write them all down and the answers will be on the next slide for you to check. This part of interpreting a scatter plot is actually beyond achieved level for this standard. It's a good to know, but not essential to know bit of information. When you look at your scatter plot, imagine two lines drawn around the scatter, like the blue lines above. What shape do the lines form? A rectangle like on the graph on the left? Or a triangle sort of fan shape like the graph on the right? The graph on the left shows equal variation across all the data values. The strength of the relationship between the variables stays the same across all the data values. The graph on the right shows unequal variation across all data values. The strength of the relationship between the variables changes across all the data values. The relationship is stronger when the explanatory variable is small, but gets weaker when the explanatory variable gets larger. Why do we care? We want to use data to make predictions. For example, remember predicting your child's adult height back on slide 6? The website could do that because it bases its predictions on data collected and the relationships in the data being analysed, just like you will be doing with scatter plots. The weaker the relationship between the variables, the less accurate any prediction will be. An outlier is a value that is much bigger or much smaller than the rest of the values in the dataset. If you have an outlier, look at the raw data. Is there an explanation relating to the context for an outlier? The graph on the right shows an unusual feature. The data appears to be separated into two groups. There is usually a reason for groups, and you can find out what that is by thinking about the context of your investigation. The graph on the right shows two groups because it turns out there were two different species of flower petals being measured. One species tended to have smaller petals than the other, and this is why there is a clump of dots of smaller measurements and another clump of dots of larger measurements. We're now going to put everything together that you've learnt in terms of relating your interpretation of the scatter plot to the context of the investigation. So on this slide here you'll see a scatter plot. What you'll first of all do is identify the shape, the direction, the strength, if there's any unusual values, and look at the variance as well. Once you've done that, you'll link it to the context. So there's an example there written in blue, and it says there is a moderate positive linear relationship between study time and quiz grade. As study time increases, the grade on the quiz also increases. So the link to the context, I'm talking about study time, I'm talking about quiz grades, always linking it back to the context, as well as having the interpretation of the scatter plot in there as well. You'll see I've used the word moderate, so that's about the strength. I've got positive, that's the direction, and linear, which is about the shape. Now it's your turn. For each of these graphs, interpret the scatter plot in terms of shape, direction, unusual values, what else? Variance, and then link it back to the context, a lot like was done on the example in the previous slide. Write down your answers and then compare them with the answers on the next slide. Check your answers that you worked out from the previous slide with the answers here. If you don't have everything that's contained in these example answers, just grab your teacher so you can get a bit more help. Follow the step-by-step instructions on the next few slides to make a scatter plot using Insight. Print your scatter plot once you have finished. A trend line fitted to your scatter plot models the relationship between the variables. You can use the trend line to make predictions. For example, using the trend line in the above graph, let us make a prediction about the calorie content of food based on its fat content. The green dashed lines are drawn from the X value up to the trend line and then across to the Y value. In this case, the X value is 22 grams of fat, and our trend line predicts that there are 700 calories in a food with that much fat. How accurate is this prediction? That all depends on the strength of the relationship. What I mean by that is how close the scatter is to the trend line. It also depends on whether there's equal variance, whether there's lurking variables, and all those other things that you've assessed before. Insight will give you an equation that mathematically describes your trend line. You will use that equation to make a prediction. The trend curve is supposed to represent the relationship between the X values and the Y values. It can be used to predict an unknown Y value based on a known X value. For example, we can predict the number of calories in food if we know how much saturated fat is in the food using the trend curve. Whether our prediction is accurate depends on how well the trend curve models the relationship between saturated fat and calories. You decide how well the trend curve models the relationship by interpreting the scatter plot, the strength, variance, unusual values, lurking variables, and shape. The equation for the trend curve is used to make predictions of an unknown Y value from a known X value. In this case, we can predict the calories if we know how much saturated fat is in the food using the trend curve equation. We use the inference information to find a range of values we predict the calories might be for a given amount of saturated fat. The trend curve uses numbers to summarize how much the Y value changes each time the X value changes. The computer puts the trend curve in a position it decides is the most fair for all the data points on the scatter plot. It tries to make the distance from the trend curve to each data point fair by putting the trend curve in the middle of all the data points. The middle is decided in the y direction, up and down. The red arrows on the graph show the distance between the trend curve and some of the data points. The green dotted line tells you that a food with 18 grams of saturated fat is predicted by the trend curve to have about 640 calories. However, there's an actual data point of a food with 18 grams of fat, and it has nearly 700 calories. The trend curve has underestimated how many calories would be in that food by 60 calories. The take-home message is strength will impact how accurate your trend curve is at predicting. See how the scatter creates a funnel on the graph above? This shows unequal variance. If the variance is not the same, the strength of the relationship between the variables changes depending on the size of the explanatory variable. When the x value is small, the relationship between x and y is strong, and the trend curve models the relationship well. This means that a prediction of y using the trend curve will be more accurate if the x value is small compared to if the x value is large. When the x value is large, there is a weak relationship between the variables, and the trend curve doesn't explain much change in the y variable. Predictions using the trend curve when x is large will be less accurate. The rest of the scatter show the general relationship between the variables. However, the outlier is affecting where the trend curve is placed, and so the true relationship between the variables is not given by the trend curve. Look at the graphs on the slide. See how the trend line moves once the outlier is removed? It becomes more steeper and is closer to the main group of dots compared to the graph that had the outlier in it. Once the outlier is removed, the trend line more accurately describes the relationship between the two variables. This means any prediction made using the trend line will be more accurate compared to when the outlier was included. You have to know though that outliers can only be removed if they're an obvious measurement error, not for any other reason. The trend curve uses numbers to summarize how much the y value changes each time the x value changes. For example, the graph on the left of the slide shows that as the fat content of food increases, so does the calorie content. The graph on the right shows that as the sugar content of food increases, so does the calorie content of food. Both fat and sugar increase the calorie content of food. Because they both influence the calorie content of food, just graphing one variable will not give us a trend line that can accurately predict the calorie content of a food, because there is another variable influencing that relationship. However, our model, the trend line, will give us a good idea of the number of calories in a food based on its fat content. When another variable influences the relationship between the two variables under investigation, we call it a lurking variable. Sugar is the lurking variable in the relationship between saturated fat and calories. Lurking variables affect the accuracy of your model and mean your prediction will not be 100% accurate. So, you've come to the end of your learning for this particular achievement standard. What you now need to do is put everything you've learnt into practice and get your skills perfected before you end up sitting the assessment. So what you'll get now is a sheet called Bivariate Data Practice Problems. It's part of your pack of notes for this particular achievement standard. Work through that, grab your teacher, ask for help if you need, refer back to this PowerPoint for help in interpreting the scatter plots, etc. And once you're ready, you can sit the assessment. Good work.